Picture this. Somewhere in the universe right now, a black hole is devouring matter at a rate that defies the laws of physics as we understood them. In November 2024, astronomers discovered a supermassive black hole called LID 568, consuming matter at over 40 times the theoretical limit, just 1.5 billion years after the Big Bang. This cosmic glutton is breaking every rule we thought governed how black holes feed, forcing scientists to rewrite textbooks about the early universe. Welcome to 100 Facts About Black Holes, the most extreme and mysterious objects in existence. These cosmic monsters bend space-time so severely that not even light can escape their grasp, creating regions where the known laws of physics break down completely. From stellar mass black holes that form when massive stars die, to supermassive giants billions of times heavier than our Sun that lurk at the hearts of galaxies, these objects continue to surprise and mystify astronomers with each new discovery. Today, we're diving deep into the science, the discoveries, and the mind-bending reality of black holes. Whether you're a space enthusiast or just curious about the universe's most extreme phenomena, these 100 facts will take you on a journey from the foundational concepts to the cutting-edge discoveries that are reshaping our understanding of reality itself. Fact 1. Black holes are regions of space-time where gravity has become so strong that nothing, not even light traveling at 186,282 miles per second, can escape once it crosses a boundary called the event horizon. This isn't just a powerful gravitational field, it's a fundamental warping of the fabric of space and time itself. The concept challenges our everyday understanding of physics and represents one of the most extreme environments in the universe. Scientifically proven, this fundamental property makes black holes truly black, as they emit no light of their own, making them invisible against the darkness of space. Fact 2. The term black hole was coined by American physicist John Archibald Wheeler in 1967, though the concept had been theoretically predicted much earlier. Before Wheeler's catchy name stuck, these objects were called frozen stars or dark stars in scientific literature. The name perfectly captures both their appearance and their defining characteristic. They appear as black voids because light cannot escape them. Widely accepted, Wheeler's terminology revolutionized how we talk about these objects, making them accessible to public imagination while accurately describing their nature. Fact 3. The existence of black holes was first predicted by Carl Schwarzschild in 1916, just months after Einstein published his theory of general relativity. While serving on the Russian front during World War I, Schwarzschild found the first exact solution to Einstein's field equations, describing what would happen if mass was compressed into an infinitely small point. His calculations revealed a critical radius, now called the Schwarzschild radius, below which nothing could escape. Scientifically proven. Remarkably, Schwarzschild made these groundbreaking calculations while suffering from a rare skin disease that would claim his life just months later. Fact 4. Black holes come in several distinct size categories, with stellar mass black holes typically ranging from 3 to 20 times the mass of our Sun. These are the most common type we've detected, formed when massive stars exhaust their nuclear fuel and collapse, Intermediate mass black holes, ranging from hundreds to thousands of solar masses, remain mysterious and rare. Supermassive black holes, found at galaxy centers, can contain millions to billions of solar masses. Scientifically proven. Scientists now also theorize about primordial black holes that could have formed in the early universe and might range from microscopic to planetary masses. Fact 5. The event horizon is the point of no return around a black hole, marking the boundary beyond which escape becomes impossible. For a non-rotating black hole, this boundary forms a perfect sphere, whose radius depends directly on the black hole's mass, about 3 kilometers per solar mass. Once anything crosses this invisible boundary, it's doomed to fall toward the singularity at the center. Scientifically proven. What makes the event horizon particularly fascinating is that, from the perspective of someone falling in, nothing special happens when crossing it. But to an outside observer, time appears to stop at this boundary. Fact 6. At the center of a black hole lies what physicists call a singularity, a point where matter is thought to be infinitely dense and space-time curvature becomes infinite. Our current understanding of physics breaks down at the singularity, as both quantum mechanics and general relativity give nonsensical predictions. This represents one of the greatest unsolved problems in physics, requiring a theory of quantum gravity to resolve. Widely accepted. Many physicists believe that singularities don't actually exist in nature, and that a complete theory of quantum gravity will reveal what really happens at a black hole's core. Fact 7. If you fell into a black hole, you would experience something called spaghettification, or the tidal effect, where the gravitational pull on your feet would be significantly stronger than on your head if you fell feet first. This difference in gravitational force would stretch you vertically and compress you horizontally, ultimately tearing you apart before you reach the singularity. For stellar mass black holes, this would happen outside the event horizon. But for supermassive black holes, you could cross the event horizon intact. Scientifically proven. This process has actually been observed happening to stars that venture too close to black holes. Fact 8. Time dilation near black holes means that time passes differently depending on your distance from the event horizon. As you approach a black hole, time for you would pass normally, but to an outside observer, you would appear to slow down dramatically, eventually seeming to freeze at the event horizon. This isn't science fiction. It's a real consequence of Einstein's general relativity, scientifically proven. If you spent an hour orbiting close to a supermassive black hole and returned to Earth, you might find that years or even decades had passed. Fact 9. The first black hole ever discovered was Cygnus X1, identified in 1971 through its X-ray emissions as it pulled matter from a companion blue supergiant star. Located about 6,000 light-years from Earth, this stellar mass black hole weighs approximately 21 times our Sun's mass. The discovery settled a famous scientific bet between physicists Stephen Hawking and Kip Thorne. Scientifically proven, Cygnus X1 continues to be one of the most studied black holes, providing crucial insights into how these objects interact with their surroundings. Fact 10. Black holes can spin at incredible speeds, with some rotating at more than 95% the speed of light at their event horizons. This rotation, called angular momentum, is inherited from the spinning star that collapsed to form the black hole, and it can be increased by absorbing matter that's also spinning. A spinning black hole, called a Kerr black hole, has a more complex structure than a non-spinning one. Scientifically proven, the spin rate affects everything about the black hole, from the shape of its event horizon to the behavior of matter in its accretion disk. Fact 11. The closest known black hole to Earth is Gaia BH1, located approximately 1,800 light-years away in the constellation of Fucus, discovered in 2022 using data from the European Space Agency's Gaia spacecraft. This black hole has a mass nearly 10 times that of our Sun and was found through its gravitational influence on a Sun-like companion star. Before this discovery, the closest known black hole was thought to be more than 3 times farther away. Scientifically proven. Despite being relatively close in cosmic terms, Gaia BH1 poses no threat to Earth and actually helps us understand how common black holes might be in our galaxy. Fact 12. Supermassive black holes exist at the centers of most, if not all, large galaxies, including our own Milky Way. These giants typically contain millions to billions of times the mass of our Sun, yet they occupy a region smaller than our solar system. How these enormous black holes formed so early in the universe's history remains one of astronomy's biggest mysteries. Scientifically proven, the relationship between galaxy mass and central black hole mass suggests these objects play crucial roles in galaxy evolution. Fact 13. Our galaxy's central black hole, Sagittarius A, pronounced A star, weighs approximately 4 million times our Sun's mass and sits 26,000 light-years from Earth. Despite its enormous mass, it's relatively quiet, consuming very little matter compared to black holes in other galaxies. We can't see the black hole directly, but we can observe stars orbiting it at incredible speeds. Scientifically proven. In 2022, astronomers released the first image of Sagittarius A, showing the glowing gas swirling around its event horizon. Fact 14. Black holes don't actually suck things in like cosmic vacuum cleaners. Objects can orbit them safely, just as planets orbit the Sun. If our Sun were replaced by a black hole of the same mass, Earth would continue orbiting normally, though we'd freeze without the Sun's light and heat. The dangerous zone is only very close to the black hole, within a few times the event horizon radius. Scientifically proven. This misconception often leads people to fear black holes unnecessarily, when in reality, you'd need to get extremely close to be in danger. Fact 15. Stephen Hawking predicted in 1974 that black holes actually emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This theoretical radiation means black holes slowly evaporate over time, with smaller black holes evaporating faster than larger ones. A black hole, with the mass of our Sun, would take 10 to the power of 67 years to evaporate completely. Widely accepted. Though Hawking radiation has never been directly observed, Its theoretical foundation is so solid that most physicists accept its existence. If you're enjoying these fascinating facts about the universe's most extreme objects, hit that like button. It really helps us reach more people who are curious about the mysteries of space and black holes. Fact chapter 16. When two black holes merge, they create ripples in space-time called gravitational waves that travel across the universe at the speed of light. These waves were first directly detected in 2015 by LIGO, confirming a century-old prediction by Einstein. The merger releases enormous energy, more than all the stars in the observable universe combined, but entirely in gravitational waves, scientifically proven. Since that first detection, scientists have observed dozens of black hole mergers, each one teaching us more about these cosmic collisions. Fact 17. The first image of a black hole's event horizon was captured in 2019, showing the supermassive black hole at the center of galaxy M87, located 55 million light-years away. This black hole weighs 6.5 billion times our Sun's mass, and the image required linking radio telescopes around the world to create a virtual Earth-sized telescope. The glowing ring in the image is hot gas swirling around the black hole. Scientifically proven. This achievement required processing petabytes of data and represents one of the most impressive technical accomplishments in astronomy. Fact 18. The most massive stellar black hole discovered in our Milky Way galaxy is Gaia BH3, found in 2024, with a mass nearly 33 times that of our Sun, located 1,926 light-years away in the constellation Aquila. This sleeping giant was discovered through the wobbling motion it causes in its companion star. Before this discovery, the largest known stellar black hole in our galaxy was Cygnus X1 at 21 solar masses. Recent discovery. This finding challenges our understanding of how massive stellar black holes can grow within our own galaxy. Fact 19. Black holes can launch powerful jets of particles that travel at nearly the speed of light and extend for thousands of light-years beyond their host galaxies. These jets form when magnetic fields around the spinning black hole accelerate charged particles from the accretion disk. Some jets are so powerful they can influence star formation in neighboring galaxies. Scientifically proven. Understanding these jets helps astronomers study how black holes affect their cosmic neighborhoods on vast scales. Fact 20. Intermediate mass black holes, weighing between 100 and 100,000 solar masses, are the missing link between stellar and supermassive black holes. These objects are surprisingly rare and difficult to detect, with only a handful of solid candidates identified. They might form from the collapse of massive gas clouds in the early universe, or from runaway collisions in dense star clusters. Recent studies suggest finding more intermediate mass black holes could solve the mystery of how supermassive black holes grew so large so quickly. Fact chapter 21. The temperature at a black hole's event horizon, as measured by Hawking radiation, is inversely proportional to its mass, meaning smaller black holes are actually hotter. A black hole with Earth's mass would have a temperature of about 0.02 Kelvin, while stellar mass, black holes, are even colder than the cosmic microwave background. Only microscopic black holes would be hot enough to glow visibly, widely accepted. This counterintuitive relationship means that as black holes evaporate and shrink, they actually get hotter and radiate faster. Fact 22. Some black holes can reactivate after being dormant for millions of years, suddenly beginning to feed on surrounding matter again. Black holes are typically either actively consuming material or dormant after swallowing everything nearby, and it's rare to observe them shifting between states. When reactivation occurs, the black hole can brighten by factors of thousands as it begins consuming new material. Recent discovery. These awakening events help scientists understand the feeding cycles of black holes throughout cosmic history. Fact 23. Quasars are among the brightest objects in the universe, powered by supermassive black holes actively feeding on surrounding matter. As matter spirals into the black hole, friction heats it to billions of degrees, causing it to shine brighter than entire galaxies. Some quasars are so luminous they can be seen from billions of light years away. Scientifically proven, the most distant quasars provide glimpses of the early universe, showing us how the first supermassive black holes formed and grew. Fact 24. Black holes can form binary systems with other black holes, spiraling around each other for millions of years before eventually merging. These systems lose energy through gravitational wave radiation, causing their orbits to decay gradually. When they finally merge, the resulting black hole is slightly less massive than the sum of the original two, with the missing mass converted to gravitational wave energy. Scientifically proven. Advanced computer simulations are required to predict exactly how these mergers unfold. Fact 25. The no-hair theorem states that black holes can be completely described by just three properties: mass, electric charge, and spin. All other information about the matter that formed the black hole is lost, which creates the information paradox, one of the most challenging problems in theoretical physics. This means two black holes with identical mass, charge, and spin are completely indistinguishable. Widely accepted. This simplicity is both elegant and troubling, as it seems to violate quantum mechanics' requirement that information cannot be destroyed. Fact 26. Micro black holes, if they exist, could be as small as subatomic particles, but would contain the mass of a mountain. These hypothetical objects might have formed in the extreme conditions of the very early universe, within the first second after the Big Bang. If they exist, they would be evaporating through Hawking radiation and might be detectable through their final explosive moments. Theoretical. Some scientists have proposed that the Large Hadron Collider might create microscopic black holes, though they would evaporate instantly and pose no danger. Fact 27. NASA researchers discovered in 2024 a tipped-over black hole in galaxy NGC 5084, rotating at a 90-degree angle relative to its host galaxy, essentially lying on its side. This bizarre orientation was hidden in decades-old data and only revealed through new image analysis techniques. The sideways black hole suggests a violent past, possibly involving a collision with another galaxy. Recent discovery. This finding demonstrates that black holes can have far more complex orientations than previously thought. Fact 28. Active galactic nuclei, AGN, are galaxies with extremely bright centers powered by supermassive black holes actively consuming matter. These can be classified into various types, including Seyfert galaxies, radio galaxies, and blazars, depending on their properties and our viewing angle. AGN can influence star formation throughout their host galaxies through powerful winds and radiation. Scientifically proven. Studying different types of AGN helps astronomers understand how black holes and galaxies co-evolve. Fact 29. The accretion disk around a black hole can reach temperatures of millions of degrees, hot enough to emit X-rays that we can detect from Earth. Matter in these disks spirals inward at different rates, with the inner regions orbiting hundreds of times per second. The friction between different layers of the disk converts gravitational energy into heat and radiation. Scientifically proven. These glowing disks are often the only visible sign of a black hole's presence. Fact 30. Scientists discovered in October 2024 the first black hole triple system, containing a central black hole with one star orbiting every 6.5 days and a second star circling at a much greater distance. This configuration challenges our understanding of black hole formation, as a typical supernova explosion should have kicked away the distant star, suggesting this black hole formed through a gentler, direct collapse process. Recent discovery. This unique system provides the first direct evidence for alternative black hole formation mechanisms. We're just getting into the really mind-blowing discoveries about black holes. If you want to keep learning about these cosmic mysteries and other fascinating space phenomena, make sure to subscribe to the channel. We release new 100-fact videos every week exploring the wonders of our universe. Fact 31. Primordial black holes might make up some or all of dark matter, the mysterious substance that makes up about 27% of the universe. These black holes would have formed from density fluctuations in the first fraction of a second after the Big Bang, before the first stars existed. They could range from microscopic sizes to thousands of solar masses. Experts theorize, if confirmed, this would solve two of astronomy's biggest mysteries simultaneously. Fact 32. The ergosphere is a region outside the event horizon of a rotating black hole where space-time itself is dragged around by the black hole's spin. Objects entering the ergosphere can still escape, but they cannot remain stationary relative to distant stars. They must rotate with the black hole. Theoretically, energy can be extracted from this region through the Penrose process. Scientifically proven. This dragging of space-time, called frame dragging, has been measured around Earth and other rotating masses. Fact 33. Naked singularities are hypothetical objects where a singularity exists without an event horizon to hide it, potentially allowing the extreme physics at the singularity to affect the outside universe. The cosmic censorship hypothesis suggests that nature forbids naked singularities, But this remains unproven. If they exist, they would let us directly observe the breakdown of physics. Theoretical. Some mathematical solutions to Einstein's equations do produce naked singularities under extreme conditions. Fact 34. Gravitational wave detections in late 2024 revealed black holes with unusual spin properties, including rapid rotation and one spinning opposite to its orbital motion, features suggesting these are second-generation black holes formed from previous mergers. One merger detected on November 10, 2024, involved black holes of 16 and 8 solar masses, with the primary black hole spinning in the opposite direction to its orbit, a first-of-its-kind observation. Recent discovery. These findings provide direct evidence for hierarchical black hole growth in dense stellar environments. Fact 5. Stellar mass black holes in binary systems can steal matter from their companion stars, creating X-ray binaries that flicker and flare as material falls onto the black hole. These systems go through cycles of activity and quiescence, sometimes lying dormant for years before suddenly brightening. The stolen matter forms an accretion disk that can outshine the companion star. Scientifically proven, X-ray binaries serve as natural laboratories for studying black hole physics and accretion processes. Fact 36. The Schwarzschild radius defines the size of a non-rotating black hole's event horizon and depends only on its mass. For Earth, this radius would be about 9 millimeters. If our planet were compressed to this size, it would become a black hole. The Sun's Schwarzschild radius is about 3 kilometers. Scientifically proven. This mathematical relationship shows that any amount of matter can theoretically become a black hole if compressed enough. Fact 37. In 2025, astronomers observed the first tidal disruption event occurring outside a galaxy's center, with a rogue black hole producing the fastest changing radio emission ever recorded from a star-eating black hole. This extraordinary discovery shows that supermassive black holes can exist and remain active far from galactic centers, challenging our understanding of where these monsters reside. Recent discovery. The event demonstrates that black holes can lurk in unexpected cosmic locations. Fact 38. Gravitational lensing occurs when a black hole's immense gravity bends light from objects behind it, acting like a cosmic magnifying glass. This can create multiple images of the same distant galaxy or quasar, or even perfect circles of light called Einstein rings. Black holes can magnify distant objects by factors of thousands. Scientifically proven. Astronomers use this effect to study both the black holes doing the lensing and the distant objects being magnified. Fact 39. Supermassive black holes can shut down star formation in their host galaxies through a process called AGN feedback. Powerful jets and winds from the black hole heat and expel gas that would otherwise collapse to form new stars. This self-regulating mechanism helps explain the observed relationship between black hole mass and galaxy properties. Widely accepted. This feedback loop means black holes play a crucial role in determining how galaxies evolve over cosmic time. Fact 40. The photon sphere is a region around a black hole where gravity is so strong that light can orbit the black hole. For a non-rotating black hole, this occurs at 1.5 times the Schwarzschild radius. Photons at this distance can circle the black hole multiple times before either falling in or escaping. Scientifically proven. This phenomenon creates the bright ring seen in images of black holes like M87 and Sagittarius A. Fact 41. White holes are theoretical opposites of black holes, regions of space-time that nothing can enter but from which matter and light emerge. While mathematically valid solutions to Einstein's equations, white holes have never been observed and may not exist in nature. They would violate the second law of thermodynamics by spontaneously decreasing entropy. Theoretical. Some physicists speculate that the Big Bang itself might have been a white hole event. Fact 42. The innermost stable circular orbit, ISCO, is the smallest orbit where matter can circle a black hole without inevitably spiraling in. For a non-rotating black hole, this occurs at 3 times the Schwarzschild radius. For maximally spinning black holes, the ISCO can be much closer to the event horizon. Scientifically proven. The location of the ISCO determines the inner edge of the accretion disk and affects the efficiency of energy extraction from infalling matter. Fact 43. University of California, Berkeley. Astronomers discovered in 2025 a massive black hole tearing apart a star thousands of light years from its galaxy's core, while the galaxy's center hosts another supermassive black hole. The central black hole weighs about 100 million solar masses and is also actively feeding on gas. This represents the first confirmed case of 2 massive black holes actively feeding in the same galaxy. Recent discovery. This discovery validates plans for the LISA space mission to detect gravitational waves from merging massive black holes. Fact 44. Black hole thermodynamics reveals surprising parallels between black holes and ordinary thermodynamic systems. Black holes have temperature, Hawking temperature, entropy, proportional to surface area, and obey laws analogous to the laws of thermodynamics. The black hole entropy formula suggests that information is stored on the event horizon's surface rather than in the volume. Widely accepted. These connections hint at deep relationships between gravity, quantum mechanics, and information theory. Fact 45. Some supermassive black holes spin so fast that they drag space-time around them at nearly the speed of light. The black hole at the center of galaxy, NGC 1365, spins at about 84% of the maximum possible rate allowed by general relativity. This extreme rotation affects everything from jet formation to the efficiency of converting matter into energy. Scientifically proven. Understanding black hole spin helps astronomers trace the history of black hole growth through accretion and mergers. Fact 46. The firewall paradox suggests that the event horizon might be surrounded by a wall of high-energy particles that would incinerate anything falling in. This theoretical problem arises from trying to reconcile general relativity with quantum mechanics and challenges the equivalence principle, a cornerstone of Einstein's theory. The paradox remains unsolved and highly debated. Experts theorize Resolving this paradox may require a fundamental revision of our understanding of space-time and quantum mechanics. Fact 47. Hypercompact stellar systems might harbor intermediate mass black holes at their centers. These dense clusters of stars show velocity dispersions, suggesting the presence of massive invisible objects. Some globular clusters exhibit evidence of black holes weighing hundreds to thousands of solar masses. Recent studies suggest finding these elusive intermediate mass black holes would help explain how supermassive black holes formed in the early universe. Fact 48. The black hole information paradox questions whether information that falls into a black hole is destroyed, seemingly violating quantum mechanics. Stephen Hawking initially argued information was lost, then changed his position in 2004. Various proposed solutions include holography, firewalls, and fuzzballs, but no consensus exists. Debated. This paradox represents one of the most fundamental conflicts between our two most successful physics theories. Fact 49. Relativistic jets from black holes can accelerate particles to 99.99% the speed of light, creating some of the highest energy particles in the universe. These jets can remain collimated for millions of light years, maintaining their narrow beam despite traveling through intergalactic space. The exact mechanism for jet formation and collimation remains partially mysterious, scientifically proven. When these jets point directly at Earth, we observe them as blazers, some of the most energetic phenomena in the universe. Fact 50. The Eddington limit describes the maximum rate at which a black hole can accrete matter before radiation pressure stops further infall. However, the black hole 568, discovered by the James Webb Space Telescope, was found consuming matter at 40 times this theoretical limit, just 1.5 billion years after the Big Bang, potentially explaining how supermassive black holes grew so quickly. Recent discovery. This discovery is forcing scientists to reconsider the physics of black hole growth in the early universe. Fact 51. Loop quantum gravity, a candidate theory for quantum gravity, suggests that black hole singularities might be replaced by regions of extremely curved but finite spacetime. In this model, matter falling into a black hole might eventually emerge from a white hole in another region of spacetime, or even another universe. The theory predicts that spacetime itself has a granular structure at the smallest scales. Theoretical. This approach could resolve the singularity problem without invoking infinite densities. Fact 52. Black holes can act as natural particle accelerators, potentially creating conditions similar to those just after the Big Bang. Near the event horizon, particles can be accelerated to energies far exceeding anything achievable in human-made colliders. These natural accelerators might produce exotic particles that could help explain dark matter. Recent studies suggest, some theories suggest, black holes could create detectable signatures of new physics beyond the standard model. Fact 53. The holographic principle suggests that all information contained in a volume of space can be represented on the boundary of that region. For black holes, This means all information about matter that fell in is encoded on the two-dimensional event horizon surface. This principle has led to major advances in theoretical physics, including the ADS-CFT correspondence, widely accepted. If correct, this principle would fundamentally change our understanding of space, suggesting that three-dimensional space might be emergent from a two-dimensional reality. Fact 54. Charged black holes, called Reissner-Nordström black holes, could theoretically exist if a black hole accumulated significant electric charge. However, in practice, black holes quickly neutralize any charge by attracting opposite charges from surrounding matter. A maximally charged black hole would have two event horizons with strange properties between them. Theoretical. The mathematics of charged black holes helps physicists explore the relationships between gravity and electromagnetism. Fact 55. The cosmic censorship conjecture, proposed by Roger Penrose, suggests that singularities arising from gravitational collapse are always hidden behind event horizons. If false, naked singularities could exist, potentially allowing observation of physics breakdown. Despite decades of research, the conjecture remains unproven. Experts theorize. This principle, if true, protects the universe from the unpredictable effects that naked singularities might cause. Fact 56. Wormholes are hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes. While allowed by general relativity, traversable wormholes would require exotic matter with negative energy density to remain open. Some theories suggest rotating black holes might naturally form wormholes. Theoretical. Though purely speculative, wormholes continue to fascinate scientists as potential shortcuts through space-time. Fact 57. Black hole mergers can produce a kick that ejects the resulting black hole from its galaxy at speeds up to thousands of kilometers per second. This happens when the two merging black holes have unequal masses or spins, causing gravitational waves to be emitted asymmetrically. Some black holes may be wandering through intergalactic space as a result. Scientifically proven, these kicks can be strong enough to overcome the gravitational pull of even massive galaxies. Fact 58. The membrane paradigm treats the event horizon as if it were a physical membrane with electrical resistance, viscosity, and other properties. This approach, developed by Kip Thorne and others, allows physicists to calculate black hole behavior without dealing with the complexities inside the event horizon. The membrane appears to have properties similar to ordinary matter. Widely accepted, this framework has proven remarkably successful in predicting observable black hole phenomena. Fact 59. Fuzzballs are a proposed alternative to traditional black hole structure in string theory, where the entire region within the event horizon is filled with tangled strings. This model eliminates the singularity and potentially resolves the information paradox. Each black hole would be a unique quantum state of strings, theoretical. If correct, black holes would be far more complex quantum objects than general relativity suggests. Fact 60. The Penrose process theoretically allows energy extraction from rotating black holes by exploiting the ergosphere. Particles entering the ergosphere can split, with one part falling into the black hole with negative energy, while the other escapes with more energy than the original particle. This could theoretically power advanced civilizations. Theoretical. While never observed naturally, this process might occur in black hole jets and accretion disks. Fact 61. Quasi-periodic oscillations, QPOs, are regular variations in X-ray brightness from black hole accretion disks, occurring on timescales of milliseconds to minutes. These oscillations provide information about the space-time geometry near black holes and can be used to measure black hole spin. Different types of QPOs may originate from various regions of the accretion disk. Scientifically proven. QPOs serve as precision tools for testing general relativity in the strong field regime. Fact 62. Magnetic field observations of our galaxy's central black hole, Sagittarius A, in 2024, revealed organized magnetic structures similar to the much more massive M87 black hole, hinting at a possible hidden jet that hasn't been observed yet. The similarity between these vastly different-sized black holes suggests universal processes governing black hole magnetic fields. Recent discovery. This unexpected finding might mean our galaxy's quiet black hole is more active than we thought. Fact 63. Extreme mass ratio in spirals occur when a stellar mass object slowly spirals into a supermassive black hole, emitting gravitational waves for thousands of orbits. These systems will be prime targets for the future LISA space mission, providing unprecedented tests of general relativity. The smaller object traces out the space-time geometry around the larger black hole. Scientifically proven. These systems could reveal whether supermassive black holes have the properties predicted by Einstein's theory. Fact 64. Some black holes may have formed directly from collapsing gas clouds in the early universe without ever being stars. These primordial black holes could have formed from rapidly collapsing pockets of gas, providing seeds for today's supermassive black holes. This direct collapse scenario could explain how supermassive black holes existed when the universe was less than 1 billion years old. Recent studies suggest evidence for this formation mechanism is accumulating from observations of the early universe. Fact 65. The gravitational redshift near black holes causes light climbing out of the gravitational well to lose energy and shift toward longer, redder wavelengths. For light escaping from just outside the event horizon, this redshift approaches infinity. This effect has been observed in light from stars orbiting Sagittarius A, scientifically proven. This phenomenon provides a direct test of Einstein's equivalence principle in extreme gravitational fields. Fact 66. Black hole shadows are the dark regions we see when observing black holes, larger than the event horizon itself due to light bending. The shadow's size and shape depend on the black hole's mass, spin, and our viewing angle. For a spinning black hole, the shadow appears asymmetric and D-shaped. Scientifically proven. The Event Horizon Telescope's images of M87 and Sagittarius A show these shadows directly. Fact 67. Intermediate mass black hole candidates have been found in unexpected places, including the outskirts of galaxies and in dwarf galaxies. These discoveries challenge models of black hole formation and growth that predict intermediate mass black holes should be rare. Some may be remnants of the first generation of stars in the universe. Recent studies suggest finding more of these elusive objects is crucial for understanding the black hole mass spectrum. Fact 68. The spin of supermassive black holes can be measured using the reflection spectrum of X-rays from the inner accretion disk. Iron atoms in the disk produce characteristic emission lines that are broadened and skewed by relativistic effects, encoding information about the black hole's rotation. Some black holes spin at over 90% of the theoretical maximum. Scientifically proven, these measurements reveal the history of black hole growth through accretion versus mergers. Fact 69. Tidal disruption events can produce light echoes as the initial flash of radiation illuminates surrounding gas clouds. These echoes arrive months or years after the initial event and provide three-dimensional mapping of material around the black hole. Each echo reveals a different layer of the surrounding environment. Scientifically proven, these delayed signals offer unique insights into the often hidden regions near supermassive black holes. Fact 70. The black hole merger, G 1905-21, detected in 2019, created a black hole of about 2 solar masses, placing it squarely in the mass gap where black holes supposedly shouldn't exist. This challenges our understanding of stellar evolution, which predicts stars shouldn't produce black holes between about 65 and 120 solar masses. Recent discovery. This detection suggests either new physics in stellar collapse or that the merging black holes were themselves products of earlier mergers. Fact 71. Soft-haired black holes are theoretical modifications of classical black holes that carry additional quantum information on their horizons. This soft hair could preserve information about the matter that formed the black hole, potentially resolving the information paradox. The concept emerged from recent developments in understanding symmetries in quantum gravity. Theoretical. If confirmed, this would mean black holes are not the simple objects described by the no-hair theorem. Fact 72. Active black holes can create cavity structures in surrounding hot gas that persist for millions of years. These bubbles, filled with relativistic particles from black hole jets, can be larger than entire galaxies. They regulate cooling and star formation in galaxy clusters by preventing hot gas from condensing. Scientifically proven. These cavities represent one of the most dramatic examples of black hole feedback on galactic scales. Fact 73. The spin axis of black holes doesn't always align with their accretion disks, creating warped and precessing disks that wobble like spinning tops. This misalignment can occur when black holes accrete matter from different directions over time or after galaxy mergers. The warping creates complex observational signatures in X-rays and other wavelengths. Scientifically proven. These tilted disks help astronomers understand the chaotic feeding history of black holes. Fact 74. Quantum effects near black holes might create an atmosphere of virtual particles constantly popping into existence at the event horizon. These quantum fluctuations could affect infalling matter and contribute to the black hole's observational appearance. Some theories suggest this quantum atmosphere could be detected with sufficiently sensitive instruments. Experts theorize this quantum fuzz might hold clues to unifying quantum mechanics and general relativity. Fact 75. The fastest growing black hole ever discovered is consuming the equivalent of one sun every day, shining with the brightness of 500 trillion suns. Located billions of light years away, this monster's appetite helps explain how supermassive black holes could grow so large in the early universe. Its accretion disk is hot enough to ionize gas thousands of light years away. Recent discovery. Such extreme feeders challenge our models of how quickly black holes can grow. Fact 76. Black holes might connect to other universes through their singularities, according to some interpretations of general relativity and quantum mechanics. The interior of a black hole could theoretically spawn a new universe through a process similar to the Big Bang. Each black hole might contain an entire cosmos invisible to outside observers. Theoretical. This multiverse scenario, while highly speculative, emerges naturally from certain approaches to quantum gravity. Fact 77. Primordial black holes lighter than about 10 to the power of 15 grams would have evaporated by now through Hawking radiation, potentially leaving observable signatures. The final moments of evaporation would produce bursts of high-energy particles that might be detectable. Some scientists search for these explosion signatures as evidence of primordial black holes. Experts theorize finding such signatures would confirm both Hawking radiation and the existence of primordial black holes. Fact 78. The black hole echo phenomenon occurs when gravitational waves bounce off the exotic structure that might replace the event horizon in quantum gravity theories. These echoes, if detected, would provide evidence that black holes aren't exactly as general relativity predicts. Some researchers claim tentative detections in LIGO data. Debated. Confirming these echoes would revolutionize our understanding of black hole structure. Fact 79. Supermassive black holes can suppress cooling in galaxy clusters across millions of light years through mechanical feedback. Jets and bubbles from the central black hole heat the surrounding gas, preventing it from cooling and forming stars. This process has been shaping galaxy clusters for billions of years. Scientifically proven. Without this black hole feedback, galaxy clusters would look completely different, with far more stars in their centers. Fact 80. The final parsec problem questions how binary, supermassive black holes overcome the last parsec of separation to merge. At this distance, they've cleared out nearby stars and gas, removing the friction needed to bring them closer. Various solutions have been proposed, including interactions with a third black hole. Widely accepted. Understanding this problem is crucial for predicting gravitational wave signals from supermassive black hole mergers. Fact 81. Some black holes produce quasi-periodic eruptions, dramatic X-ray flares that repeat every few hours to days. These events might be caused by stars on highly eccentric orbits that lose matter each time they pass close to the black hole. Each eruption can briefly outshine the entire galaxy in X-rays. Recent discovery. These regular fireworks provide natural laboratories for studying matter behavior in extreme gravity. Fact 82. Black hole coronae are mysterious regions of hot plasma near black holes that produce hard X-rays. These coronae can disappear and reappear over timescales of days, completely changing the black hole's X-ray appearance. The physical nature and location of these coronae remain debated. Scientifically proven, understanding coronae is essential for interpreting black hole observations across the electromagnetic spectrum. Fact 83. The Bardeen-Peterson effect causes misaligned accretion disks to gradually align with the black hole's spin axis through frame dragging. The inner parts of the disk align first, creating a warped transition region. This process can take millions of years for supermassive black holes. Widely accepted, this alignment mechanism affects jet directions and accretion efficiency over cosmic timescales. Fact 84. Nanohertz gravitational waves from orbiting supermassive black hole pairs create a background hum throughout the universe. Pulsar timing arrays have recently detected evidence of this gravitational wave background, confirming that the universe is filled with orbiting black hole pairs. These waves have periods of years to decades. Recent discovery. This detection opens a new window for studying the population of supermassive black hole pairs throughout cosmic history. Fact 85. Black holes can create light rings where photons orbit multiple times before escaping, producing a series of increasingly demagnified images. For the black hole M87, theory predicts an infinite series of these rings, each containing a complete image of the universe. Future telescopes might resolve these nested rings. Theoretical. Observing these rings would provide unprecedented tests of general relativity and black hole physics. Fact 86. The Thorne-Jidkov object is a theoretical stellar hybrid with a neutron star or black hole at its core, surrounded by a diffuse stellar envelope. A few candidate objects have been identified, though none confirmed. These objects would have unique chemical signatures from nuclear processing near the compact core. Experts theorize finding such objects would reveal new pathways for black hole formation and stellar evolution. Fact 87. Superradiance is a process where rotating black holes can amplify certain waves that scatter off them, extracting rotational energy. This phenomenon could create black hole bombs if the waves are confined, potentially leading to observable gravitational wave signatures. Some particles around black holes might naturally create these conditions. Theoretical. This exotic process might limit how fast black holes can spin in certain environments. Fact 88. Failed supernovae occur when massive stars collapse directly to black holes without an explosion, potentially accounting for the missing red supergiants that seem to vanish without typical supernova signatures. These events might produce most stellar mass black holes, happening more frequently than successful supernovae. Recent studies suggest this quiet route to black hole formation could explain the abundance of black holes in binary systems. Fact 89. Black holes might leave observable memories in gravitational waves, permanent distortions in space-time that persist after the waves pass. These gravitational wave memories encode information about the merger and could be detected by future gravitational wave observatories. The effect accumulates over time, potentially becoming measurable. Theoretical. Detecting gravitational wave memory would confirm subtle predictions of general relativity and provide new tools for studying black hole mergers. Fact 90. A proposed mission would send a paperclip-sized spacecraft powered by Earth-based lasers to a nearby black hole within a century, allowing direct tests of physics in extreme gravity. Such a probe could measure frame dragging, test the equivalence principle, and search for deviations from general relativity. The technology, while challenging, is within theoretical reach. Experts theorize this ambitious mission could revolutionize our understanding of fundamental physics. Fact 91. The black hole at the center of galaxy M87 launches a jet that extends over 5,000 light-years, yet remains narrowly focused to less than 60 light-years wide. This jet carries more power than the combined luminosity of billions of stars, accelerating particles to 99.99% the speed of light. Recent observations show the jet wobbling over time, suggesting the black hole's spin axis is precessing. Scientifically proven. The stability and power of such jets over cosmic distances remains one of astrophysics' most impressive phenomena. Fact 92. Microlensing by stellar mass black holes can magnify distant stars by factors of thousands when they pass directly between Earth and the background star. These events last weeks to months and provide a way to detect isolated black holes that emit no radiation. Several candidates have been identified through this method. Scientifically proven. This technique might reveal a vast population of invisible black holes wandering through our galaxy. Fact 93. The shadow of Sagittarius A appears to change size when observed at different times, suggesting either rapid rotation or turbulent accretion. These variations happen on timescales of minutes, corresponding to the orbital period at the innermost stable circular orbit. Each observation provides a snapshot of the constantly changing environment near the event horizon. Recent discovery. This variability makes our galactic center black hole a dynamic laboratory for testing accretion theories. Fact 94. Black holes could theoretically be used for time travel to the future through gravitational time dilation. Orbiting close to a black hole for a few hours could result in years passing on Earth. The closer to the event horizon, the more extreme the time dilation effect. This isn't science fiction, but a real consequence of general relativity. Scientifically proven. While practically impossible with current technology, the physics is well understood and unavoidable near black holes. Fact 95. The merger of two black holes can radiate away up to 10% of their combined mass as gravitational waves in just milliseconds. For the largest observed mergers, This represents more energy than converting several suns entirely to energy. The space-time distortions from these events can be detected from billions of light years away, scientifically proven. These cosmic collisions are the most energetic events in the universe since the Big Bang. Fact 96. The Einstein ring around the cosmic horseshoe galaxy revealed what may be the most massive black hole ever found at 36 billion times our Sun's mass. Discovered through gravitational lensing effects 5 billion light years away. This monster exceeds theoretical predictions for how large black holes can grow through normal processes. Recent discovery. Such ultramassive black holes challenge our understanding of the limits of black hole growth. Fact 97. Black holes might quantum tunnel to become white holes after enormously long timescales, potentially resolving the information paradox. This process would take far longer than the current age of the universe, but could represent the ultimate fate of black holes. The transition would preserve information while appearing as an explosion of matter and energy. Theoretical. This speculative idea connects black holes to the deepest questions about time, causality, and information. Fact 98. The sound of black holes has been extracted from pressure waves in the hot gas surrounding them. The Perseus Galaxy cluster black hole sings a B-flat note 57 octaves below middle C. These acoustic waves, while inaudible in the vacuum of space, create ripples in galaxy cluster gas that astronomers can detect and convert to sound. Scientifically proven. These cosmic songs help astronomers understand how black holes inject energy into their surroundings. Fact 99. Hypervelocity. Stars traveling at over 1,000 kilometers per second can be ejected from galaxies by close encounters with supermassive black hole binary systems. These stars become intergalactic wanderers, carrying planetary systems with them on million-year journeys through the void. Dozens of such stars have been discovered fleeing our galaxy. Scientifically proven. These stellar refugees provide evidence for binary supermassive black holes and violent dynamical processes in galactic centers. Fact 100. The ultimate fate of black holes depends on whether protons decay. If they do, black holes will be the last objects in the universe, evaporating through Hawking radiation over unimaginable timescales of 10 to the power of 100 years. In this scenario, black holes would outlive everything else, slowly shrinking as they radiate away their mass until they explode in a final burst of energy. The universe would end in a cold, empty state punctuated only by these occasional flashes from dying black holes. Theoretical. This black hole era represents one possible endpoint for cosmic evolution, where these gravitational monsters become the universe's final inhabitants before darkness claims everything. We've journeyed from the foundational physics of event horizons to the mind-bending frontiers where our understanding breaks down. These 100 facts about black holes reveal objects that are simultaneously simple and incomprehensibly complex, described by just 3 numbers, yet harboring mysteries that challenge our most fundamental theories of reality. From Gaia BH1, lurking just 1,500 light-years away, to monsters billions of times more massive than our Sun, Black holes shape the universe on every scale imaginable. The discoveries we've explored today showcase how dramatically our understanding has evolved since Carl Schwarzschild first calculated their theoretical existence in 1916. The detection of gravitational waves confirmed Einstein's century-old predictions while opening entirely new ways to study these cosmic enigmas. The first photographs of black hole shadows transformed them from mathematical abstractions into visceral realities. And recent discoveries like LID 568's impossible feeding rate and the first black hole triple system continue to shatter our assumptions about what these objects can do. What makes black holes truly extraordinary isn't just their extreme physics, it's how they connect to the deepest questions in science. The information paradox forces us to confront the incompatibility between quantum mechanics and general relativity. Primordial black holes might explain dark matter. The interiors of black holes might spawn new universes. These aren't just astrophysical curiosities. They're natural laboratories where the fundamental laws of physics reveal themselves in their most extreme forms. The practical implications extend far beyond theoretical physics. Supermassive black holes regulate galaxy formation, determining where and how stars form across cosmic history. Their jets inject energy on scales that dwarf human comprehension, influencing regions millions of light-years across. Without black holes, the universe would look completely different. Galaxies might not exist as we know them, and the cosmic web of matter would have evolved along entirely different paths. Looking ahead, the next decade promises revolutionary advances in black hole science. The Event Horizon Telescope continues improving, potentially revealing movies of matter swirling into oblivion. The LISA mission will detect gravitational waves from merging supermassive black holes, unveiling a hidden universe of cosmic collisions. Next-generation ground-based telescopes will track stars orbiting black holes in distant galaxies. And perhaps most excitingly, quantum gravity theories might finally explain what happens at the singularity, resolving paradoxes that have puzzled physicists for generations. The story of black holes is ultimately a testament to human curiosity and ingenuity. Using mathematics, physics, and increasingly sophisticated technology, we've managed to understand objects that by definition cannot be directly observed. We've turned the universe's most extreme environments into tools for testing our theories and expanding our knowledge. Every new discovery raises more questions, driving us deeper into the fundamental nature of space, time, matter, and information itself. These cosmic monsters that once seemed like mathematical curiosities have become central to our understanding of the universe. They've taught us that space and time are malleable, that information might be the most fundamental quantity in nature, and that the universe is far stranger than we ever imagined. As we continue exploring these gravitational giants, one thing remains certain. Black holes will keep surprising us, challenging our assumptions, and pushing the boundaries of human knowledge for generations to come. Thanks for joining me on this incredible journey through 100 facts about the universe's most extreme objects. If you found these revelations as mind-blowing as I did, please hit that like button and subscribe to the channel. Your support helps us create more deep dives into the mysteries of space, from the quantum realm to the cosmic web. Share this video with anyone who's curious about the universe's most enigmatic phenomena. What facts surprised you the most? Let me know in the comments below. I love hearing which discoveries capture your imagination. And remember, we release new 100-fact videos every week, exploring everything from ancient civilizations to cutting-edge technology. Until next time, keep looking up and questioning everything about our amazing universe.